Dear student, so today or in this video lecture we will discuss a new topic on physical properties. Okay, so in the last video we discussed about the general method of preparation for haloalkanes and haloarenes, and today in this video we will study about the physical properties. We will discuss chemical properties later. So there are two parts, physical and chemical behaviors. So in physical property or in physical behavior we will discuss three physical properties related to haloalkanes and haloarenes, and these are melting point, boiling point and solubility. So first of all we will discuss about boiling point. Okay, boiling point or BP in short. So you all know what is boiling point. Boiling point is a temperature, is a particular temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Okay, so technically or in terms of physics we say that when vapor pressure is equal to the atmospheric pressure, that temperature at which at the particular temperature at which we get this balance is called boiling point. So today we will discuss that depending on the structure how boiling points varies in haloalkanes. Okay, so boiling point, we will discuss boiling point variation in haloalkanes only. Okay, so you have to remember that there are 2 points you have to remember. First, with increase in molecular mass, boiling point of haloalkanes increases. Okay, so with increase in molecular mass, boiling point increases. In this topic or in the physical property, most of the time you will be asked, reasoning questions are being asked. Okay, so we will discuss the reasons. Okay, why with increase in molecular mass the boiling point increases. So the reason is because with increase in molecular mass, van der Waals force of attraction also increases. Okay, so what is the reason behind increase in boiling point? So the reason is that with increase in molecular mass, the van der Waals interaction or the London forces between two molecules increases, and as a result the molecules are tightly packed, so it takes more energy to separate them, so boiling point increases. That means chloroethane will have a higher boiling point than chloromethane because it has a higher molecular mass. Similarly, if we compare, it has a higher boiling point as its molecular mass is higher. And suppose now if we consider iodoethane, then we can see iodine has a bigger molecular mass, so this molecule has a higher molecular mass, so as a result it will have a higher boiling point. Okay, sorry, so iodoethane will have higher boiling point than chloroethane because its molecular mass is higher. So in general this is the order for boiling point. Okay, if we fix the number of carbons in alkyl chain, and if we keep on changing our halide part, then from fluorine to iodine boiling point increases as iodine has highest molecular mass. Okay, so this was the this was the first point or the first case. Now we will see another case. The another case will be related to R. That means suppose if we change the alkyl group, if we take different alkyl group and same halogen, okay, that means if we take fluorine as fluorine in all the cases, chlorine in all the cases, and if we change the R. So in second case we will discuss about for isomeric, okay, mind it, it's for isomeric. For isomeric haloalkanes, the order of boiling point is 3 degree, 2 degree, 1 degree. That means two degree, 1 degree. That means 1 degree haloalkanes will have higher boiling point and 3 degree haloalkanes will have lower boiling points. Okay, so let us take an example. Suppose this is 2-chloro-2-methyl propane. Okay, now suppose we take, if we take okay, so this is a, as you can see, this is a 2 degree carbon, so this is 2-chlorobutane, okay, 2-chlorobutane. So 2-chlorobutane is a 2 degree haloalkane. Now we can have a 1 degree haloalkane also in a single chain like this. So this is a 1 degree haloalkane, okay, or chloroalkane. So if you compare the boiling points, they all have the same molecular formula. As you can check, they have 4 carbons, in total 9 hydrogens and 1 chlorine. Okay, you can check in all the molecules they have total 4 carbon, 9 hydrogen and 1 chlorine, so they all have same molecular mass. And what we discussed in the first point, if the molecular mass changes, the boiling point changes, but here the molecular mass is not changing, but still their boiling point will change. It will have the lowest boiling point and it will have the highest boiling point. Okay, so actually now we discussed about the fact that it will have the highest boiling point and it will have the lowest boiling point, but from exam point of view, the fact is not the important part. The main thing that we should know is why this molecule has a lower boiling point. Okay, so after knowing this fact, let's discuss about the reason. Okay, what is the explanation? Okay, so just observe carefully. Okay, explanation is the most important part. Most of the time, the questions are asked like 2-chloro-2-methyl propane has a lower boiling point than 1-chlorobutane. Why? Okay, so you will ask questions like this. So what will be the explanation? The explanation is, with increase in branching, you have seen in 3 degree haloalkanes we have more branches. Okay, so with increase in branching, the surface area of the molecule decreases. As a result, its boiling point also decreases. So that's the reason. What happens if more branches are there? Okay, so what is happening in one chlorobutane? We have a straight chain. It has a longer surface area, and in 2-chloro-2-methyl-propane you can see that because of the branching, the molecule is more or less spherical. It has a smaller surface area. For smaller surface area, we need less energy to separate the molecules. Okay, so due to this lower surface area, the boiling point of branched alkanes or branched haloalkanes is lower than the non-branched haloalkanes. Okay, so keep this explanation in mind, and you can use the same writing, this particular statement for all the questions. Okay, like suppose here we have written with increase in branching, the surface area of the molecule decreases, as a result its boiling point decreases. So suppose I give you a question related to 2-chloro-2-methylpropane and 1-chlorobutane. So you can write 2-chloro-2-methylpropane has a lower boiling point than 1-chlorobutane because, and this is statement. So it's a generic statement you can use for almost every question related to boiling point. Okay, so you can construct the answer easily. Now we will go to the next physical property. Okay, and the next physical property is melting point. Okay, melting point. Now obviously you all know what is melting point. Again, melting point is that temperature at which anything changes from solid phase to the liquid phase. Okay, from solid to liquid, and something growing from solid to liquid, it has a different mechanism than liquid to gas phase. What happens when something changes from liquid phase to gaseous phase? The intermolecular separation between the liquid increases. Okay, but for anything to convert from solid to liquid, it has a different mechanism. What happens? Solids are arranged in small crystal lattices. Crystal lattice structure you will study in solid state, chapter 1 chemistry in details. So these small crystals, we need to break these crystals in order to take the molecules out. Okay, and only then we can convert something from solid to liquid. So that means the basic idea about melting point is related to this crystal structure. Okay, how better this crystal is. If the crystal structure is better, we will have a higher melting point, and if the crystal structure is not that good, then we will have a lower melting point. So the melting point is related to, we study actually in our syllabus, we study melting point question related to haloarenes, like boiling point. In boiling point section we discussed haloalkanes. In melting point section we will discuss haloarenes. So let's check. So what happens, suppose we have 3 different type of disubstituted chlorobenzene. Okay, so it's easy to understand that this one is ortho-chlorobenzene. Okay, or 1,2, the IUPAC name is 1,2-dichlorobenzene. Okay, similarly you can check that this is 1,3-dichlorobenzene, or with respect to this chlorine, this is a meta position, or with respect to this chlorine is in meta position. So it's meta chlorobenzene and this is para chlorobenzene. This chlorine is in the para position. So we have a ortho isomer, meta isomer and para isomer, and we want to know that out of these 3 isomers, which will have the higher boiling point, melting point, and which will have the lower melting point. Actually what happens, there is no remarkable difference of melting point between ortho and meta isomer. They are almost same, but there is a remarkable difference of melting point between the meta and ortho and para isomer. Okay, these two have a very lower melting point, and para isomers have very higher melting point compared to the ortho or meta isomers. And why is that? Why para isomers have considerably higher melting point than the meta or ortho isomer? So this is the fact. Like the previous topic, we will discuss the explanation part. Okay, why is it so? So let's go to the explanation part, and it's very easy. Just stick to the basic definition or stick to the basic concept. What we talked about the crystal lattice. That means anything which can form a better crystal will have a higher melting point. So what happens? The explanation, I will write down the explanation. What happens? Due to symmetrical structure, of para isomers, it can fit better into the crystal lattice. Okay, you understand? You see, if I have random objects, suppose I have this marker ink, I have this pen, I have this duster, it's very difficult to arrange them together because they are of different size and shapes. But suppose if I have 3 marker pens, I can arrange them very easily and in a very ordered manner, okay, because they are symmetrical. So symmetrical objects are very easy to adjust. Since para isomer is quite symmetric, it's exactly symmetrical structure. We have a chlorine here, we have a chlorine here, so it's completely symmetric structure, so it fits very good in the crystal lattice. And as a result, since it can form a better crystal lattice due to its symmetry, it has a higher melting point. Okay, so due to symmetrical structure of the para isomers, it can fit better into the crystal lattice and hence will have a higher melting point. Okay, so now these two topics I have covered. So what you have to keep in mind? First, you have to keep in mind that what are the facts, how boiling point changes, means if you change the the halogen part, how boiling point will increase or decrease, and what is the reason? The reason is when we change the halogen part, the reason is molecular mass. Okay, when we change to the isometric alkanes, the reason is surface area. Okay, with increase in surface area, the boiling point decreases. And when we talk about the melting point, the reason is symmetrical structure. So the reasons are very important because most of the time explain why type questions are being asked from this part. Okay, so now we will move to the next part. It's our last topic in physical properties, and it's the solubility. Okay, solubility. So whenever in our syllabus, whenever we will discuss solubility, by default you have to understand that we are checking the solubility in water. Okay, in class 11 chemical bonding part, I have told you, we discussed earlier, that water is a polar molecule. Okay, it has a permanent dipole. Okay, permanent dipole structure, and since due to presence of this dipole, water molecules are polar molecule. So water is a polar solvent. Okay, so what we are trying to do, we are trying to find out the extent of solubility of haloalkanes or haloarenes in water. In order to check the stability, what we have to do, we have to understand that we have a CX bond. We have a CX bond, okay, carbon halogen bond present in the haloalkane. And apart from that, this halogen is connected to alkyl chain or aryl chain. For haloarenes, it's benzene ring, okay. Now, see, in previous chemistry classes, you already know that we have a concept which says like dissolves like, okay. That means a polar solvent will dissolve a polar molecule and a non-polar solvent dissolve a non-polar molecule, okay. So the thing is, in order to check the solubility of alkyl halide, we have to check whether the alkyl halide is polar or non-polar. In the previous topic, I have discussed that CX bond is definitely a polar bond, okay. Due to difference in electronegativity, this CX bond is a polar bond. So does that mean that haloalkanes are highly soluble in water? Well, yes and no, both. What happens? Actually, due to this polar bond, it gives haloalkanes a better opportunity to dissolve in water. But the thing is, this alkyl part is totally made up of carbon and hydrogen, and all the bonds in the alkyl parts are non-polar. And alkyl chains, generally alkyne chains are very hydrophobic in nature. What is hydrophobic? Anything which repels water, okay, which is not good with water, okay. Phobia, you know, like phobia. So it alkyl chains generally do not go well with water molecule, okay. So what happens? You will see a mixed, you know, trend in the solubility. What happens? Lower alkyl halides or haloalkanes are fairly soluble, okay, are fairly soluble in water. Okay, now you understand what is lower alkyl halide? Lower alkyl halide means where number of carbons is less, okay, that is lower alkyl halide. So what happens? In lower alkyl halide, the alkyl chain is small, that means hydrophobic part is small. So the polar part, the CX polar part predominates and it is fairly soluble in water. As we go to the higher alkanes, okay, as we increase the number of carbon, that is higher alkyl halides, okay, the solubility, obviously the solubility will what? Decrease, okay, the solubility will decrease. But you have to keep in mind that I am talking about the solubility in water, okay, in water. I am not talking about any organic solvent yet. We will discuss about organic solvents also, like benzene, okay, or carbon tetrachloride, okay. So generally they are highly soluble in organic solvents, okay, in organic solvents. And why they are highly soluble in organic solvents? The reason is alkyl halide itself is an organic molecule, so it interacts very well with other organic solvents. And most of the time organic solvents are primarily the organic solvent that we use are benzene and carbon tetrachloride, and both the molecules are non-polar in nature. So since they are non-polar, so what happens, higher alkyl groups tend to dissolve better in these non-polar organic solvents. Okay, so this is all about the solubility. Okay, so in solubility, and I discussed in class 11 few things about how you can determine the polarity of a molecule. Okay, you can determine the polarity of a molecule by using hybridization, concept of hybridization, and the difference of electronegativity. Combining both the concepts, you can determine whether a molecule is polar or not. So if a molecule is highly polar, obviously it will dissolve in molecule like water, which is already a polar solvent, and if it is not a polar solvent, a polar molecule, then it will go to the non-polar solvents or organic solvents. Okay, it can also dissolve in organic acids also. So today's we have discussed the complete topic. Okay, so we are done today. So what you have to do, you have to go through these topics in NCERT in detail. The notes will be provided and the questions will also be provided. Okay, and just keep the explanation part in your mind, keep them checked.